And speaker is Sami Douba, and he's going to tell us about dense embeddings with hyperbolic manifold theory.
Thank you for the invitation to speak. I'm going to be talking about joint work in progress with Konstantinos Tsouvalas, and the goal, at least, I mean, hopefully I will accomplish this goal, but anyway, the goal will be to embed the fundamental group of a closed hyperbolic 3 manifold into SL4R densely. Okay, so first you might ask why. The answer is because it's fun. You might also ask why I'm starting with dimension 3, the dimension of the manifold. And I mean, one answer is that this is a conference on 3 manifolds, but another answer is that surfaces have already been done for us. So it's a theorem of Pleyard, Gielander, Soto, and Storm that any semi-simple, well, connected semi-simple Lie group contains a dense copy of contains a dense surface subgroup. And in fact, you can replace this with any non-abelian limit group. So in fact, if you know what that is, then great. And so this is kind of remarkable. But by work of Sela, these do not, I mean, closed hyperbolic 3 manifold groups are not limit groups because they do not split over cyclic subgroups. It's visible from the boundary of such groups, for example. But I will say that the arguments here are bare arguments, and the strategy that I'm going to describe for you can be adapted to produce surface subgroups that are a bit more tangible than these. So you can, I mean, if you like surfaces, you can just pretend I'm thinking about a surface group. So instead of using this, instead of using bare arguments, we'll use the following standard fact. Let's say G is an R group, which is to say that it's cut out by polynomial equations with real coefficients, such that the identity component of the R points of G is simple. And simplicity is really key here. If gamma is Zariski dense and indiscrete or non-discrete, then gamma is in fact topologically dense, not just Zariski dense. Okay, and the proof is straightforward. I'll write it here. So first of all, it's well, you consider the normalizer of the identity component of the closure of gamma. This is a topological closure of gamma in G. And this is algebraic. This is just because, so maybe I'll give it a bold symbol. And this is an algebraic or a Zariski closed subgroup of SLN, and that's because you can interpret this subgroup in terms of Lie algebras, and the action of SLN on the adjoint action of SLN on its Lie algebra is algebraic. This is how you deduce this fact. But and now, well, This is true because the identity component of a Lie group is always normalized by the Lie group. It's always a normal subgroup. In particular, gamma is in here, but gamma is Zariski dense. So in particular, this Lie group is normal in here, but this has positive dimension since gamma, by assumption, it's indiscrete. But G is a simple Lie group, so I'm being intentionally vague, but I'm assuming it's Zariski dense in bold G, which by definition, that's how one defines Zariski dense in yeah. But thanks. Yeah. Okay, and then we're done. So this is the tool we're going to use, and the strategy, the general strategy, is first we start with uniform or co-compact lattice in this Lie group. So this is a notation from Michel's mini course last week. This is here, Q is some quadratic form of signature 3, 1. So you can think of this as a subgroup of GL4, in fact, SL4 plus minus. So this means I'm allowing both positive and negative determinants, which is convenient. So this is you can think of this as a subgroup preserving a two-sheeted hyperboloid. But now this plus indicates that I want this group to preserve each sheet, which and each sheet then becomes a model of, in fact, the so-called hyperboloid model of hyperbolic tree space. But it doesn't matter which quadratic form of this signature you pick, you always get an identification. So at the moment, gamma is neither, it's neither indiscrete nor Zariski dense in here because it's trapped in here. So the goal will then be to bend gamma. These are known as Johnson-Milson deformations to make gamma Zariski dense in SL4. And okay, now we're one step closer. We have something Zariski dense, but it's still going to be discrete, in fact. And then we Galois conjugate. The example I'm going to give you is arithmetic, but it doesn't have to be. Yes, this will be essential. Yeah. I think it's possible that I think it's not known if some of these lattices are super rigid in higher dimensions. I will explain. Yeah. But the point is that if gamma was Zariski dense before Galois conjugation, then it will still be Zariski dense after Galois conjugation. Okay, so that's the general strategy. So what's the example? Take lambda to be this, and maybe I'll write it like this, a subgroup of this group. So this is, I'm just writing, this is a diagonal matrix that I'm just writing as a row where phi is the golden ratio. So again, we saw this form last week in Michel's mini course, and by email correspondence with Nick Brody, the principal congruent subgroup of lambda of level 2 is the reflection group isom H3 corresponding to the right-angled dodecahedron. And so in particular, this matrix is a reflection in this group. So this is the reflection in a wall, call it pi, of a dodecahedral tile. I'm bad at drawing three-dimensional pictures, so I'm going to draw the picture one dimension down. And I'll draw it in the Klein model. So hyperplanes are projective hyperplanes in this model. Blue's not good. Well, okay. So I have a tile that looks like this, and I'm just going to double the group across pi. And this doubled group will be my gamma. The point is I want to create something along which I can bend. So if this reflection is tau, then I know exactly what this right-angled reflection group. So, well, okay, all right. Gamma will be the double. I mean, okay, that's maybe bad. Well, gamma is this group. So delta will be this group. And here's its reflection. So delta is the group generated by the reflections in all other walls of the dodecahedron. So it's, I mean, you should think of it as the fundamental group of an orbifold with totally geodesic boundary. And maybe I'll give these, I'll rename delta, well, delta 1. And its conjugate delta 2. And it's somehow clear from this picture that gamma in fact splits this way, where delta naught is the intersection of these two groups. It's the group generated by all walls orthogonal to pi. So gamma is still a uniform lattice. And now we're going to deform the inclusion. So for define a family of representations as follows. This representation will be induced by the identity on the first factor, but on the second factor we'll conjugate by a matrix GT, where GT is this matrix. So this is a matrix in GL4, but GL4 normalizes this group, and this matrix commutes with delta naught. So I mean, I should say centralizes delta naught, and so this is a well-defined representation. And so for some values of t, this representation will be garbage. Okay, well, if maybe first I should say if t is equal to 1, then we recover the inclusion. That's maybe not so interesting. If t is equal to -1, we get an unfaithful representation. It's this representation. But the claim is that when t is positive, rho t is faithful. In fact, it's also discrete for all such t. Maybe a few words. So first of all, the fact that this representation is faithful for t very close to 1, let's say, this follows already from the work of Kosul in the late 60s, but also, I mean, philosophically, it follows from stability of Anosov representations, for example. The fact that this is true for all positive t, also, I mean, because we're working with a reflection group here, it in fact follows from work of Winberg from the early 70s. It's very easy to check that Winberg gives you faithfulness. It also follows from later work of Benoit, but I'm going to give a very elementary argument that we learned from Jean-Philippe Durel. And it's just a ping pong argument. So here's the Klein model of H3, and here's my distinguished hyperplane. So I'm thinking of this picture as living in projective 3 space. So, I mean, all these groups act on projective 3 space via the embedding here. You can define 2 sets, P1, and this is P2. And the point here is that these sets are invariant under this stretching. So what this map does is that it stretches horizontally. And these will be our ping pong sets. So
Can I ask you about the dimensions of the various objects in this cartoon?
yes.
So the ball in the middle is actually a 3 ball. Right?
Yes. Mhm.
And what's to the left? Is that like a 3 ball cross interval?
What's here is a cone. I mean, there's a point at infinity that you're not seeing at which these 2 things meet. It's a point dual to this blue hyperplane. No, P1 is this entire P1 is this entire cone.
So the cone is 4-dimensional.
The cone is 3-dimensional in this. Yeah.
I think I'm thinking you said P.
Yeah. This.
That's
Yeah. Maybe that's. Yeah. No, that's maybe better. Yeah. So I mean, now we leverage our understanding, our geometric understanding of this group, right? And now I'm going to draw a wider ellipsoid because it doesn't matter how wide it is. Now, if I take any, yes, let's say, yeah. So now, if I take any element in delta 2 that's not in this blue subgroup, what will it do to P1? Well, it will map it somewhere, but in particular, it will map it to the interior of P2. But that means that if I take any element in this amalgam that's not in the blue subgroup, then it has to map this point at infinity dual to this blue hyperplane to the interior of one of the PIs. But that means that the representation is faithful. U pi to the, interior. And so in fact, this argument tells you more. It tells you that not only is this representation faithful, but it's hyper faithful in the sense that it maps no non-trivial element to a unipotent. Because it suffices to check. Let's say elements here whose normal forms have even length, and then you can check that such a word has to map one of the PIs strictly into its interior. And unipotent elements can't do that. So that's kind of interesting. Okay, so another fact is the argument clear? I like this argument. So also, when t is not plus or minus 1, rho t is Zariski dense in SL4. I'm not really going to explain why this is true, but this follows essentially from Zariski density. Sorry, from Zariski density of delta in this group. So the fact that this group alone, without blue, is Zariski dense, gives you Zariski density of this deformation. Yeah, so it's somehow easier, but yeah, also this group is maximal, and this does not normalize it. So but you can really just prove it by hand. Okay, so we're almost there. Now, by the claim, rho sub phi, for instance, again, phi was the golden ratio, is faithful. Zariski dense. I mean, well, by this remark. And now Galois conjugate. So what do I mean? I mean, this representation will be dense, where sigma is the non-trivial element of this Galois group. And again, it's Zariski dense because this representation was Zariski dense. It's faithful because this representation was faithful. I mean, we did nothing to the representation algebraically, but now this representation is topologically dense, and it's a nice explicit representation. Yes, yes. So in fact, you can refine this argument to also give you discreteness. Yeah. In fact, these are all in also. Sorry, I forgot. Thank you. So I mean, why is this not discrete? Well, okay, maybe I'll is not discrete since oh well, I just erased it, but the image of this subgroup is pre-compact. I mean, in fact, the image of I mean, even I mean the image of this entire thing is pre-compact. So this is why it's not discrete. Hence, this representation is as desired. Well, okay, if you want something in SL4, you pass to a torsion. I mean, and you want a manifold group, you pass to something torsion-free and orientation-preserving. However, I don't like this argument so much because well, the issue is what if we started with a group that was defined over the rationals, let's say, maybe something like this, say. This is also a uniform lattice, by the way. I mean, also, maybe you want to embed non-uniform lattices, but let's just stick to uniform lattices for now. In fact, this is also a reflection group, CF Nick Brody. So let me give you an alternative strategy that also works in this case. So the fact that this works for all t tells us that it works in particular for some transcendental positive t. So claim implies rho t is faithful for some transcendental positive t, but then it's also faithful for negative t, negative transcendental t. Thus, rho t is also faithful all transcendental non-zero t. Wait, sorry, is this what I want to say? Wait, so I made a mistake earlier. I said that this representation was faithful when t was, I mean, this representation is the inclusion when t is the identity, is 1. Sorry, this representation is the inclusion when t is 1, and it's not faithful when t is -1. Okay, I always get confused at this point. So why is this true? For the same reason that this representation remained faithful. So you can, I mean, so say, maybe I'll give this a different designation. Rho T naught is equal to rho T sigma, where sigma is a unique isomorphism of fields fixing gradical 5 and mapping T to T naught. Right, this field automorphism will do nothing to these gammas, but it will change GT to GT naught. Okay, so now take a sequence of transcendentals T1, T2, so on in R approaching -1. Then eventually this representation, remember it's still faithful, but eventually it's not discrete. This follows from the following other standard fact. Say gamma is a discrete group. I'm just thinking, yeah. All of whose normal nilpotent subgroups are finite. I'm saying discrete here because soon I'm going to endow Hom gamma G with the compact open topology. So it's just a group. So I mean, what are examples of such groups? Of course, any Gromov hyperbolic group has this property, and like really any hyperbolic-like group has this property. Also, Zariski dense subgroups of semi-simple Lie groups have this property, and our gamma happens to be both of those things. And let G be any Lie group. Then the set of discrete and faithful representations in the space of representations from gamma to G is closed. So, yeah, the proof, I mean, to prove this, you look in Raghunathan's book. It's a standard fact. I can talk about it more if people want, but in fact, all we're using, which is even easier, is that if you take a limit of discrete and faithful representations, that will be faithful. We're only using faithfulness of the limit. Okay, so this eventually has to be indiscrete. Why? Because otherwise we would have that. Otherwise, rho sub -1 would be faithful, since it would be a limit of discrete and faithful representations. But this rho sub -1 is not faithful. Okay, so yeah, again, rho sub -1 was this representation. Any questions?
You know the faithfulness of all sub T or T algebraic and negative?
So I mean, what I wanted to say next is that, of course, you did not need to pick T transcendental. I mean, so you can also adjust this argument to give you I mean, a dense representation with algebraic entries. If you want, I can. Here, let's do it. Yeah, so the advantage of this geometric strategy is that you only use algebra at the last step, and so you only use like baby commutative algebra. So and also use this strategy to produce dense embeddings with algebraic entries. For example, since this ring is dense, in R, you can always find a sequence like this, where the an and bn are integers, such that this sequence approaches 0 and up to and negating, passing to a subsequence. You can assume, what do I want to assume? I want to assume, hopefully this is correct, that an is positive and bn is negative. Maybe I want to say here that these are not 0. So in this case, in particular, bn will have to go to minus infinity, and now set Tn to be this quantity. Okay, so the point is we want to mimic what's happening over there, but with algebraic numbers. So this approaches -1, but its Galois conjugates are eventually wait. Is this what I want? Yes, its Galois conjugates are eventually positive, right? Since bn is blowing up in the negative direction, where sigma is the element of this Galois group that maps radical 2. I mean, it negates radical 2 and fixes radical 5. And so here again, rho sub Tn is eventually indiscrete and faithful and dense, since the group, I mean, after you, yeah, I mean, this will not be plus or minus 1. And maybe one more thing about these representations is because we knew that these discrete representations were not only faithful, they mapped no non-trivial element to a unipotent. The same will be true of their Galois conjugates. So you can really say a lot about these dense representations. Okay, and so this is a very general strategy. In particular, you now have all the tools to prove the following theorem. I mean, maybe you had them before I started talking. I don't know. Let gamma, maybe I'll just call it isom H3 or isom Hn, be a uniform lattice whose commensurator contains a reflection. And as Mahan suggested, we do this because we want to have things along which we can bend. Then for any m larger than n, there's a finite index subgroup that depends on m, such that gamma m embeds densely in SLMR. And maybe I'll just say a few words about what kinds of gamma can appear here. So this, I mean, includes uniform arithmetic gamma of simplest type. And Michel defined these lattices last week. In fact, these are precisely the arithmetic lattices in here that contain reflections in their commensurators. Also, of course, uniform reflection lattices. That much is clear. But also all the Agel lattices by their very construction. Also, at least, yes, I mean the inbred ones, yeah. But also at least some Gromov-Piasecki-Shapiro lattices. Why is that? Because you can construct. Well, okay, maybe I won't explain this, and I'll just explain how one how one does this. So let's try to embed a surface group densely in SL5. So let's increase the difference between the dimensions. Okay, how do we do this? So the first step will be to create something first, then to get the risky density in some group that's very close to SL5, for example, in O41. So start, for example, with, wait, let's create more hyperplanes. Say we start with a right-angled hexagon. Here's the hexagon. Okay, this is virtually a surface group. And now we bend. In fact, you might call this tilting instead of bending. And you get something Zariski dense in isom H3 now. And now you can repeat this one dimension higher. Zariski density is already detected by, I mean, Zariski density in O31 is already detected by 4 reflections. So you can now think of, maybe you have a picture like this now on the boundary of H3. So you should think that you actually have spheres sitting on top of these circles, and you have a plane coming out here. And you can bend this plane. Then you get something Zariski dense in O41. So here we, this is Zariski dense in O31. Okay, and now we're very close. We have something Zariski dense in O41. Again, Zariski density is detected by 5 reflections. So there will be 1 reflection remaining along which we can double and bend in SL5 as we did in the first example. Okay, that's all I wanted to say. Thank you. So for the first example, not at all. Here, I'm using uniformities to say that I can tilt. But maybe there's, I mean, I'm not saying that this is, I mean, it's possible you can also bend in SLN. It's just hairier. So I mean, we haven't really considered that yet. I mean, yeah, I guess all these groups embed in compact Lie groups by I mean, okay, by many names, but Bertrand, Hagelin, Wise, Wise, Agel, other Agel, another Agel. I mean, the same Agel, but another. Yeah. So, but that's as much as I mean, for yeah, of course, the lattice that we started with today can be Galois conjugated to a compact Lie group, and I sort of implicitly use that fact. But I don't know if that answers your. Yeah. I mean, yeah. So something I could have added to the abstract of this talk was that I was considering non-compact Lie group because I wanted to play this. I wanted to leverage geometry. So I don't know. Yeah. I mean, I'm using the fact that I mean, okay, what is Gromov-Piasecki-Shapiro function as far as I'm concerned? You start with some orbifold, well, two orbitals that actually typically look something like this. Then you have another one. looks like this, and then you blue, but you still have some, so, okay, what is this? I mean, this orbifold has reflection, singularity, I'll just indicate them by in comic books, people want to say that the power, but the power there. But also you can use the separability to create little days over here and blue, and you still have those similarities.